Right. Okay. Yeah. So similar idea to yesterday. Try and keep it like fairly light and informal. Do ask questions as we go along. There are going to be little breaks where you can try and follow along on your laptops if you've got your laptops and you've got things installed. And we will have a break for coffee sometime between 10 and 11, regardless. Okay. So yesterday I tried to kind of cover the very basic ideas of functional programming, how that relates to parallel programming, and give you a little glimpse of Scala. So we got that done yesterday. So this morning I want to cover Haskell, Jealous, and Dex. And well, we'll see why as we go along. But actually, just out of interest, who's got these things installed on their laptop? Who thinks they have working Haskell installed on their laptop? Yeah, quite a few. Brilliant. Who thinks they have a working JAX of some description installed on their laptop? That's lots. Who's got Dex installed on their laptop? Well, very good. Well done. Those people who managed to install Dex. It's a little bit tricky to install, but that's fine. That's perfect. Cool. Right. So we'll start off with Haskell then. So Haskell is like the cool functional programming language that all theoretical computer scientists love. So if you think it's controversial to say to statisticians that R is rubbish, try saying to a theoretical computer scientist that Scala is better than Haskell. That's real controversy for you. But Haskell is like the old strongly typed functional programming language, but it has this interesting wrinkle that is good and bad, in that it's a lazy language by default. So it defers evaluating anything as long as it possibly can. And part of the reason for the development of Haskell was to prove that it's possible to have a programming language that is lazy by default, and that it's perfectly possible to have a perfectly working general purpose programming language that is entirely lazy by default. It proved that point, but that doesn't necessarily mean that it's better for all purposes to have a language that's lazy by default. And I think actually a lot of serious theoretical computer scientists now believe that on balance, for a general purpose programming language, strict evaluation by default is probably better. It just leads to more predictable memory usage, more predictable runtime performance characteristics, etc. So although it's kind of interesting that it's lazy by default, it can be a bit of a pain in some situations as well. Okay, right. So, but again, you'll see lots of similarities with Scala. So if you've got it installed, you should be able to just run GHCI to give you a REPL, just like the Scala REPL, and you should be able to start typing stuff in as and when you go. So here's some examples. So you can just start pasting these into the REPL. So if I go to Ubuntu, here I've got a little Haskell REPL, and if I just start pasting stuff in, you'll see what happens. Okay, so what was I wanting to say here? Yeah, so like Scala, it's a strict, strongly typed language, but it has type inference. Okay, so it infers types, but it does it slightly differently to Scala, and in particular, it will defer evaluating numeric types as long as possible, which can be very powerful, but can also be a bit confusing. So in Scala, if you said y equals 6, it would see that the 6 was an integer, and the type inferred would therefore be integer. Okay, whereas Haskell wants to be clever, and when it says y equals 6, it says, well, y is a number, but I don't know if that's really supposed to be an integer or a double or whatever. So I'm going to defer deciding what type that number is until I have further evidence. Okay, and so that can sometimes be a bit confusing, but can sometimes be useful. Okay, so the type inference, much like Scala, but the way it's implemented is slightly different, and there are pros and cons with it. Yeah, so in the REPL, you can just use :T to get the type of something, and that's very handy.
How do you read the type of line here? What is it? Read line?
Yeah, so this means that the type class is numeric of type P, and so if you give a P, you'll get a P. So I mean, just read it as numeric. but the type is yet to be filled in. Yeah, so that P will one day be int or float or double. Yeah, so it's a numeric type, but we haven't said exactly what the numeric type is. But one day when it knows the type, we will get the type and it will be an int or a double. Yeah, so it's a deferred type. Okay, well, so we can do that. So let's keep going. It has immutable collections, just like Scala. Again, Haskell is a very old language, so when it was created, everybody thought linked lists were brilliant, and linked lists are very cool, but unfortunately, they have they don't parallelize well, right? So one of the problems with Haskell is that it has linked lists built in a very fundamental way around the language, but they don't parallelize particularly well. So you don't actually want to be using linked lists for everything, especially if you're doing parallel computing. So again, looking at the syntax here, I'm saying that this list here, so just using square brackets tells you that it's a list, a linked list. So yeah, people know a linked list is just basically like a stack that you can push things on the front and pop things off the top. It's got lots of efficient traversal operations. So like popping something off the top and pushing something on the front is an order one operation, but lots of operations are obviously going to be order there. Yeah, and don't necessarily parallelize because all you know is the link to the next element of the list. Okay, so we denote types with double colon, and so this is a list of integers. Okay, so the int is in square brackets, so that means it's a list of integers. Okay, so that L is a list of integers, and indeed, if we ask what the type of L is, it says L is a list of integers. Okay, so that's how we read that type. But as I say, linked lists don't parallelize very well. So again, we have these immutable arrays that are very, very similar to the vector type in Scala. Is that all going to work? Yeah, that didn't work. And so we do all the same tricks we did in Scala. We can say, okay, so LA is going to be a list array. But then if we update an element, so we change the element at position 1 to be 7, we get the new list where the element at position 1 is being changed to a 7, but the old list still exists. Okay, it's very much like the vector type in Scala. Okay, so this is one of these immutable data structures. I think it's implemented in a very similar way to the vector type in Scala. So it's basically a binary tree, but with big blocks at the leaves, which are a bit more cache friendly than having a pure binary tree. Okay, so we can map things. So we can use fmap. Actually, this is something Chris asked about yesterday. Why is map the other way around? So in Haskell, you apply the fmap function to a function and a list. And it's that way round because you might want to say, well, it's just carried a particular way round, which is convenient sometimes and not others. Because you sometimes want to, simplify things, you can use this infix notation for mapping. So that means map the function on the list L. It's still the other way around to Scala, of course, but that's the way around it is. You can fold left and fold right. Obviously, if you've got an associative operation, they will give you the same result. If you don't have an associative operation, they won't. Yeah, they have different performance characteristics, but probably that's not worth exploring. We can write functions. It's a bit funny writing functions in the REPL, so don't worry if you get some warnings or whatever when you start pasting stuff in the REPL. But that's how we could define a log factorial function. So again, just reading the code there. We first of all say what the type signature is, right? So these are your Haskell type signatures. So log fact has type int to double. Okay, so that tells you that log fact is actually a function. It's a function that maps integers to doubles. Getting used to reading these Haskell type signatures is kind of useful. And if any of you have used JAX at all and you've tried reading JAX documentation, you'll see that slightly curiously, all of the JAX documentation uses Haskell type signatures to tell you what the JAX functions do. Okay, so understanding how to read these Haskell type signatures is handy. So log fact maps an integer to a double, and then we just have to specify the function. And we say, well, log fact applied to n will give you such and such, and uses what's called pattern matching. So you don't have to define the function all in one go. You can define it to apply to certain things. Okay, so here we're only dealing with ints, so we could just say what it has to do with an int. But if you had a more complex data structure that it acted on, you could just pattern match on bits of that data structure and just say how the function acts on, you know, particular parts of that data structure separately. Okay, so it's a bit irritating to have to write out log fact again. It seems a bit weird, but there is a reason for it. So you can define your function in pieces. But anyway, yeah, so you're going to sum the result of mapping log over the numbers from 1 to n. Okay, so that all makes sense. So that's obviously not recursive. The way, well, in fact, it will be recursive when it actually gets implemented because you're mapping over a linked list, so that will recurse. But it's not obviously recursive, but we can write an obviously recursive version here. So again, the type signature is the same, but we're now saying, well, if n is 0, we're going to return 0. Otherwise, we're going to add the log of n to the result of running log fact on n minus 1. Okay, so that's our recursive version. And the from integral thing there is, again, because of this deferred type inference, we need to make sure we get something that we can take the log from.
The issue concerning tail recursion and scalable.
So this is where it all gets very subtle, because Haskell is lazy by default. And so what that means is that there are lots of situations where in a strict language you would blow the stack, but actually if you're carefully evaluating a lazy recursive call, you don't. Okay, and so in fact, you don't have the same issues that you have in Scala. So this is one of the advantages of a lazy model, that actually recursive functions typically don't load the stack because they're evaluated lazy. Yeah. So you don't need to worry about that so much. On the other hand, the performance characteristics aren't as good as the strict versions necessarily. So there are swings and roundabouts. Yeah, so there we go. In fact, so this is due to Haskell's lazy evaluation. Actually, can I make that? Oh, it's because I'm in Ubuntu, isn't it? Let's go back to Windows. Yeah. So you don't need to worry about Stack Overflow as much, but it can be a little bit mysterious whether you do need to worry about it or not. So you can certainly do tail recursive things in Haskell. So there's an example. So this is very much like the example we did in Scala, where we have a function called log fact, so log fact3, but inside that function we have another function called go, which actually does the evaluation, and that function called go has a second argument, which is going to be our accumulator. Okay, and so we just set it away with the right initial value, and on. That makes sense. I'll use as a where clause. Okay, so yeah, so we're just defining the function go using the where clause there. So we introduce it, then define it, which again is a bit backwards in some languages, but we just say, okay, we're going to call on back by calling this function go, and now I'm going to tell you what the go function is. Okay, and you just define it by saying how it operates. So this is an example of pattern matching. We first of all say what go on at 0 and some accumulator does, and then we say what go on an arbitrary n the accumulator does. Okay, and the pattern matching does happen sequentially. So if you've matched on 0, you won't match on n. Okay, but you Obviously, you're not always going to match on that first line because the n is always going to be 0, but you will match on the second line because both of those are determinants, so it's always going to match on the second line, and so you just do there to recursive call. Okay, so hopefully that makes sense. So the syntax is different from Scala, but the ideas are really quite similar. The slightly weird thing about Haskell that people either love or hate is that everything is fully curried by default. So if we have this example we looked at in Scala yesterday, doing creating a function that returns a linear function. So you know, you see y equals mx plus c, but the idea is you pass in the m and the c, and you get back the function that maps x to y. Here, if you look at that Haskell type signature, it's a little bit mysterious because it's double to double to double to double, but that's okay. You just pass in as many arguments as you like, and it gives you back the result, which is a function of the desired length. And so if you pass in 2 parameters, well, you've specified the first 2 parameters, so what you're left with is a double to double, so that's what you're going to get back. You're going to get back a function that maps the double to a double. Okay, and so you can then call the function in the usual way. Okay, so in Haskell, typically everything is fully curried like that. Can make it hard to read the type signatures, but does allow you to write, you know, clever pieces of code. Okay, so it's kind of.
Yeah, in this example, presumably the order really matters.
Yes.
So would it be possible, say, to input just the intercept before the slope?
It is, but of course it wouldn't be as convenient. Okay, so you would actually then have to write a new function that just partially applied that second function. So you can do that in any of these languages, right? You can put in arguments, but it's more cumbersome. Yeah, so you define a new function that specified the second argument but left the first one indeterminate. So you could write the function to do it, okay, but it's much more convenient to pass them in the order that they're current, right? And so that's why you kind of have to think about the order that you place your arguments. Yeah.
Just a comment really, but this isn't just like a Haskell thing. This comes directly out of Lancaster.
Right.
So it's not like an arbitrary thing in the Haskell. It's done.
Yeah, but there's still a choice, right? Because it is your choice whether you think that this is a double to double to double, say, or a pair of doubles to a double, right? That's always a choice. How much you curry or uncurry is always a choice. The order you curry your arguments is always a choice. So yeah, absolutely. It all goes back to the lambda calculus, but there is still kind of good syntax and bad syntax. And it's kind of interesting because the language we're going to look at next started off almost exactly like Haskell and has gradually evolved to more Scala-like notation. So that's kind of is an interesting observation. But anyway, that's your type signatures. So yeah, it's always true, right? That maybe I'm just assuming things that I shouldn't be. But you know, if you've got an x to y to z, okay, that is equivalent to x cross y to z, okay. But you think of them differently, because in the first case you think about x giving you back a function from y to z, and in the second case you think about supplying an x and y and getting back a z, right? So they're equivalent. So going this way is called currying. Haskell curry, going this way is called uncurrying. And although I didn't show you this in Scala yesterday, there is a method called curry and uncurry. So you can take a function that is not curried and call curry on it, or you can take a function that is called uncurry on it, and it will do this transformation.
Sorry, can I ask another question?
Yes.
And also with this chain of like arrows, is that operation associative? Do you see, can you put brackets in that?
Yes and no. So you can put brackets in it, but that can sometimes change what it means.
Okay.
But
the meaning is still unambiguous.
The meaning is unambiguous. So conceptually, obviously, function chaining is associated. I'm a bit worried when I'm saying this now, because it's not the same as function composition, which definitely is associated. It is a bit different, but it definitely changes things. So, for example, if you put brackets around the final double to double, which you absolutely can do, right? Then it is different because it means you can't just supply the first three arguments. Okay. So if you really put the easiest way to do this is to play around with it in the record, right? You can put brackets around things, but that can change. Like, for example, actually, so a better example would be putting brackets around the first two. Then the first argument would have to be a function that maps the double to a double. It couldn't be a double, yeah? And so it can change the way that you use the function. So this is why I'm a little bit nervous about making strong statements. But you absolutely can put brackets around, and that does sometimes change how you interpret the signature. Okay. So that was that. So let's have a look at an example. Right, so we've got this little running example of gradient ascent on a logistic regression model. And so it's in the repo, so you can look at it, but I'll just call it up here so you can look at the main bit of code. So again, Haskell has lots of build systems, just like Scala has lots of build systems. So this build system I'm using here called Stat is very much analogous to the build system SVT we looked at with Scala yesterday very briefly. So it's a Stat project that expects various things in various directories, and then it will do lots of clever things for you. But the kind of main file that you're interested in is this main.hs. So if we just look at that. Okay, so Haskell is a bit different to Scala in that it relies quite a lot on what are known as language extensions, whereas Scala doesn't in the same way. Scala mainly relies on you doing things with libraries and not actually radically changing the library using library extensions. But that's a bit of a simplification because Scala has a macro system that actually can be used to change the way the language works a little bit without formally requiring language extensions. And you can have compiler plugins in Scala as well, which also do similar things to language extensions. So, these bits at the top are what's known as language extensions. But the idea is you've got a module main. We're going to have imports just like you would in Scala. So they're just extending the namespace. We've, just like in Scala, got a bit of boilerplate to read in the data and get our X and our Y. So let's not worry about that. Yeah, and then there are lots of different types that you can use. So here I'm using a library called H-matrix to do basically numerical linear algebra. So again, this links to a fairly efficient sort of BLAST type backend. But the way you write it is a little bit different to Scala, but you get the idea. You can sum a double. So I've written a little function to sum a vector of doubles because that didn't seem to be built in. So there's an example of how you could do that. Basically, you just dot product a vector of ones. So that's not necessarily very efficient, but that's a way you could sum a vector. There's our log likelihood. Again, I could probably have written it slightly more neatly than that. In this library, matrix vector multiplication is hash greater than. And you've got to be a little bit careful with minus signs in Scala and in Haskell. Sometimes you just need to negate things rather than stick a URI minus at the front, which is a bit irritating, but you can live with it. So that's the log likelihood, the gradient similar. So I guess the more interesting things is looking at how we do the gradient descent. And again, there are lots of ways you could do this, but the way I've chosen to do it here is that we have a function of one step that does one step of your gradient descent. For that, you've got to pass in the x and the y, and also the learning rate, and then you will get back a function that maps your old parameter beta to your new parameter beta. Okay, so again, it's not totally obvious from the function signature, but the intention is that you first of all pass in 3 parameters and then get back a function that maps a vector of doubles to a vector of doubles. So that's your one step. Then the actual function to do the ascent is here. So you see here I have put brackets around the first 2 arguments there, because I want the first argument to be this function that performs one step of gradient descent. So that's why I put brackets around the first 2 arguments. So that's what I'm going to pass in. And then I'm going to pass in an init and some, tuning parameters. And then I'm going to call go with that init, the maximum number of iterations. And then I'm going to define the go function on the fly inside the ascend function. And that's going to do essentially the same as the Scala version did. I'm going to start off. I'm going to do one step. I'm going to check my convergence criterion. And if it's met, I'm going to return my final beta. Otherwise, I'm going to call this function again with the number of iterations decreased by 1. So I think that function is kind of fairly clean and self-explanatory. There's also this business about dollar in Haskell. So that means because the precedence, if you didn't have the dollar there, you'd have to put brackets around the B1 minus B0, otherwise it would get confused about whether this was 1 or 2 arguments. And so you put dollar there to mean that has lower precedence than the stuff on the right. You could just put brackets around it, but Haskell people tend to prefer to use dollars rather than put brackets everywhere. I don't like brackets everywhere.
Sorry. Why did you need to say let on minus? This is big.
Because I want to refer to B1. So you know how in Scala you can declare bars and vowels, yeah? So the let is a bit like declaring a vowel. I'm going to say I want B1 to be the result of calling a step on B0.
Okay.
And then in the rest of that block, I now have something called B1 that I can refer to. But it only exists within the confines of that let block. Yeah. So again, in Haskell, the idea is to not create loads of variables all over the place, and to, when you do create variables, to limit their scope. Okay, so this is kind of a Pascal-y thing to do, where yeah, you say I want to be able to refer to this thing called B1 in this block, but I only want it to be defined within the scope of that block, because once I've finished with that block, I don't want it polluting the next stuff. Okay, and then there's stuff that we don't have time to talk about, which is that at some point you've got to do input and output, and input and output isn't a pure function. And so how do you do that in a pure function language? And Haskell really forces you to agree about this. And basically, you've got to carry out everything in the IO command, and I don't really have time to explain that properly. But basically, you do the input in this inside this IO monad, then call your program to do all of the real work, and then you come back to the IO monad to output your results at the end. Yeah. So in the context of most statistical applications, this final main block is usually very small, because all of your work is done by regular functions, yeah, you just read in your data, call your function to do all the work, and output the results. So again, it works much the same way. So if I go back to Ubuntu, should be able to just run this. Need to change my timeout on this. So what did I say? Oh, this is the crash course. Yeah, exactly. So it should just be that. Come out the REPL, do stack, build. That is what was it? And it runs. Okay. So that is that. Okay, so next. Yeah, so do people want 5 minutes just to have a little play around with this, or would people rather just move on? Okay, well, maybe I'll just move on. So that was Haskell. So I didn't say anything specifically about parallel programming here. I don't think it's particularly necessary. It's kind of interesting that Haskell will just randomly parallelize things when it feels like it, right? Because it's a pure functional language, so it knows which computations can be done in parallel. And so if the compiler decides, well, actually, there's this stuff going on and that stuff going on, and it can all be done in parallel, well, maybe I should parallelize that. So in fact, recent versions of the Haskell compiler will just, decide to run your code in parallel if it feels like it and can figure out how. However, you'll generally find that Haskell is not as fast as the other languages we're talking about today. And so maybe this wouldn't be the first choice for doing really kind of intensive scalable computation anyway. But it's still useful to know because, as I said, all of the kind of stuff people write online about functional programming, a lot of it uses Haskell for its examples. As I mentioned, the JAX people are obviously very strongly influenced by Haskell. A lot of their documentation uses Haskell type signatures. You want to read blog posts about monads, they're all written using Haskell as the example, etc. So if you're going to do any functional programming, it's worth knowing a little bit of Haskell and being able to read Haskell code at least, and Haskell type signatures, etc. Because it will just make accessing the kind of world of functional programming documentation much easier. But I wouldn't necessarily recommend it for parallel programming or doing stuff on GPUs, etc. So you absolutely can use it to do that. And as we see, DEX is actually written fast, so I mean it's definitely possible. But it wouldn't be my first choice. Right. Okay. So that's Haskell. So we've done a little bit of Scala, a little bit of Haskell. They're both general purpose functional programming languages. Now we're going to look at JAX, which is a Python library but it's essentially a pure functional language embedded in Python, but it's a pure functional language that is specifically aimed at doing tensor operations and autodiff on tensor operations. Okay, so it's limited in its scope. It's not a general purpose programming language, but it's very good at what it does. And in particular, it automatically parallelizes things to run on multiple cores on your CPU, or if you have a GPU and you have the GPU version enabled, it will also run things on GPU. And it's generally considered to be the fastest of these things. Okay, so TensorFlow, Torch, they're kind of competitors in this space, but JAX are generally considered to be faster. And personally, I think it's just a much cleaner, better designed language than those two as well. So the idea is it's supposed to just feel like Python, right? So you just replace NP with dot with JNP dot, and you replace SP dot with JSP dot and, you know, all your code is kind of the same. But of course it isn't, because Python isn't a functional language and JAX is. So there's a lot more to it than that, in fact, in practice. But as you'll see, once you understand the principles of functional programming, it's all actually incredibly straightforward. So again, most of you, I think, already have this up and running, but you'll see that a JAX array is very much like a Scala vector or a Haskell immutable array. Okay, you define your array. We're going to set it here to be float 32. So lots of machine learning people like 32-bit stuff, because it runs faster on GPUs generally. Personally, I'm always a little bit wary of 32-bit because it does lead to more numerical problems. But there we are. If you want to go fast, then go 32-bit. But they're immutable, just like Scala vectors and Haskell immutable arrays. So if we say do this, we can look at the second element. We can set the element at position 2 to be 7. But then when we look at those two arrays, the updated array, okay, has the thing changed to a 7, but the original array still exists and has it still set to a 6, right? So it's exactly like those immutable data structures we use with Scala and Haskell. Okay. Semantics are all the same. I don't actually know exactly how these things are implemented and how much they avoid copying, etc. But I suspect they're doing similarly clever things to the Haskell and Scala. Right, yes.
Can you repeat usually I'm familiar with pointers, and when you change an element in an array, it kind of point to that element and then change the element if it's a mutable, like how the pointers works in a functional languages.
So what have we got? 2, 4, 7, and 3. I'll use this. We've got 2, 4, 7, and 3. Now, this isn't exactly how they're implemented, but conceptually, they're just living in a binary tree, right? And if you now say, I want to change, oh, well, just say we want to change this to, I don't know, 3. How do we do that? Well, the point is, most of this tree we can keep, okay? The only bits that we have to kind of change is this link here. This link here. It's kind of this link here and this link here. And the rest of the tree we can kind of keep as it was, yeah? So we can just take the whole of that tree, the whole of that subtree, and we just replace those two links to build the new tree that has this bit from before. It has this subtree from before, and the only thing that's new and different is this, which now has to point to this new tree that actually has a 3 here. Yeah, and so most of the tree is not copied. Yeah, and it's safe to do this because these numbers are never going to change because it's immutable.
Also, when you have a functional programming language, it's the same, right? So if you just but you point to an array and then change elements in an array, it changes also the other array because it's pointing at it. Oh,
no. Well, I mean, obviously you can, right? So you can have mutable data structures. So in Scala, you choose, do you want mutable or immutable data structures? By default, you're always given an immutable data structure, okay. But you can have mutable data structures for sure. But you're not really doing pure functional programming if you use those. Yeah, but this is actually a really crucial thing to understand, that you don't have to copy everything. Now, like I said, the way these things are implemented, these leaves at the bottom aren't actually individual values, they're blocks of values because they then are much more cache friendly, right? So there is a little bit of copying of the blocks at the bottom, right? So it's not as simple as I'm describing it here, but that's purely for performance reasons. Conceptually, this is what's going on. And there are lots of these immutable data structures, right? This is an example of an immutable data structure, but there are huge numbers of these things that are well studied, and their performance characteristics are all well studied and well understood. So conceptually, that's what's going on here. Exactly how it's implemented in JAX, I really don't know. Okay, so what do we know that we can do with these immutable data structures? Well, we know that we can map them, and we know that conceptually that can happen in parallel, because if we're mapping a pure function, then clearly all of these things are independent of one another, they're not interfering with one another, and so if we've got lots of processes, we can just divide up the work between all the processes that we have and do bits of work separately on different processes, okay? So that parallelizes, and JAX will do it all the time. So if you're working on CPU, it will parallelize over your cores. If you're working on GPU, it will just distribute it to the cores on your GPU. Okay, so that's good. And we can also reduce. And again, as we've discussed, reduction can happen by a tree reduction. So again, if you've got lots of processes, that basically goes from order n to order log n. So that happens in parallel as well. Okay, so you notice how the reduce function in JAX expects you to have a 0. Okay, so not only are you required to have an associative function that you're reducing with, you're also expected to have a 0. So we're absolutely back in the world of monoids. Okay, so monoids just are everywhere in functional programming. Okay, so you can do this with any monoid. It doesn't have to be just numbers. Any monoidal structure you can reduce. And there are some convenient methods like summing that can be done, okay? But it must be monoidal, and if you pass in a function that is not associative, then the result is undefined. Okay, so you can define functions, and the defining functions is more or less like Python, just using Python syntax. However, there is this annotation you can apply that will JIT compile this function, but running more efficiently. Now, it's a little bit mysterious as to when you need this annotation and when you don't, because some things will get automatically JITted whether or not you put this annotation on. But to be on the safe side, if you're not sure if it's going to get automatically JITted, just shove the JIT annotation on. That doesn't usually slow things down. And yes, but inside a JITted function, everything has to be JAX code, right? You can't have regular Python code inside JAX JITted function. And so another reason for putting the JIT annotation on is to check that you're doing sensible JAXy things inside this function. So inside this function, all we're calling is that reduce function. That's obviously a JAX thing. So it's perfectly fine to do that. But what we couldn't do is stick the float command inside that function. So say we didn't actually want to return the result of this as a kind of JAX vector containing one element. We actually wanted to just return the float. Actually, you can't directly do that because float is a Python command, not a JAX command, and so you can't JIT that.
To be able to create a lambda function that would be Python code.
Sorry?
You use the lambda function that would be Python code. That's right. So I guess I'm wondering what values are. That's just something kind of change to the JAX. The phrase Python.
Yeah, no, it's exactly, and this is why it's a bit confusing programming JAX, because this is something that JAX doesn't understand. So JAX understands lambdas. So a lambda basically is just a Python expression, and you can use regular Python expressions inside JAX code. What you can't do is use Python functions necessarily. Now, what is a function and what is a Python expression is sometimes a bit unclear. But yeah, it's a good point. But lambda is okay. Okay, JAX understands lambda, so you have those inside the JAX code float. You can. Okay, so now we get the real interesting thing that in most general purpose functional programming languages, you use recursion a lot, okay, because you don't have regular for loops, regular while loops, etc. So for traversing data structures, you need to always use recursion. However, there are issues with general recursion. if you're wanting to do things on GPUs, or especially if you're wanting to auto-diff code, it can be a little bit tricky to reverse mode differentiate through recursive functions, etc. And so actually, some of these tensor-oriented languages actually forbid you from using recursions. So then you're kind of in trouble, right? Because you don't have regular variables, regular mutable variables, and you don't have recursion. So how on earth do you do anything? And the answer is you're given some constructs that you are allowed to use. Okay, so MapReduce and scan, the usual thing, they're built in. Okay, so you can use those. That's fine. But you're also given some built-in constructs, Jack's while loop and Jack's for I loop, which kind of serve the same kind of purpose as a regular for loop or a regular while loop in other languages, but they're not the same, right? They are restricted in what they do and how they work in a way that they're not in an arbitrary, say, Python code. Okay, so you use while loop to do a while loop type thing. Okay, so that is an iteration where you don't know statically the number of iterations you're going to use, or you use a for I loop and one repeat. You do know how many iterations you want to do, but they're not exactly the same as a Python for loop or while. Because it's hard to reverse mode differentiate. So you can forward mode differentiate through, say, a while loop. That's not a problem. But obviously, for efficiency, you typically want to reverse mode differentiate. So especially like scalar valued function, you absolutely want to reverse mode auto diff. And it's quite hard to reverse mode auto diff if you don't know like how deep your function trace is going to be. And so so you can't do that. So for a while loop, you can't reverse mode auto diff through it. But the for I loop you can. Okay, so if you need reverse mode, you really need to figure out how to write it as a for loop. And if you really need a while loop, then you've only got forward mode on. So if we want to do our log factorial function, we're all intimately familiar with now, we can do this with a for loop. Okay, so we start with 1, we terminate at n, it's usual Python exclusive termination criterion, so we write n plus 1 if we want to terminate at n. And then we've got our lambda function that is what is going to execute at each stage of the loop. Okay, and that requires an I, which is your iteration counter that the for loop construct will provide for you, and an accumulator, which you are also allowed. So you see it's very similar in structure to the kind of way we wrote this in the pure functional language using recursion for fairly obvious reasons. And the kind of logic is that we take our accumulator and we add the log I to it. Okay, and we initialize the accumulator. It's the last argument. Okay, so you see that it's given this thing called a for I loop, but in fact, if you compare it to the Scala or Haskell code we wrote, it has a very, very similar structure to that recursive function that we use, where we explicitly pass an accumulator through the function. Yeah, so that's where this all comes from, right? This is why I think it's really quite hard to learn JAX if you've never done any functional programming in a regular functional programming, because it will all look totally mysterious, right? Where on earth did any of this stuff come from, right? Whereas if you learned a little bit of functional programming first, it's all kind of natural. So there we go. There's our for I loop. I think that's relatively straightforward.
Maybe the float, a function, you say that you're not allowed to use it in Java. The float in front of the return. You didn't use it.
Yeah, I didn't JIT it. Yeah.
Okay, so this is not going to be JIT.
So that probably won't JIT. Yeah, it's a good point. That probably won't JIT. You could try. But you know, that is a good point, that probably won't JIT. And so, yeah, you probably would prefer to write that slightly differently so that it would JIT. Right. Yeah, and so you can do the same thing with a while loop. Obviously, we don't need to use a while loop here, but this is a good way of sort of illustrating how a while loop can be used. It's a bit more complicated because we're propagating these two items of state, right? So in the for loop, that was sort of given by the construct that you kind of were expected to provide a lambda that took a counter and a piece of state and did something with it. Whereas if you're going to use the while loop, it's up to you what you propagate through. But here we obviously need to propagate through both the counter and the accumulator. So we're going to call that state, and we're going to have to like pack and unpack that state at each step through this while loop. Okay. So again, the main kind of logic is in the advanced function, where we unpack the state to be an I and an accumulator. We then add 1 to I and update the accumulator. And that's how we advance the while loop. Our continuation criteria is embedded in the cont function, which again unpacks the state and checks whether we're finished. And then the final line, again, wraps a float around it, but says while loop, my continuation criterion is given in the function cont, my advanced function is given in the function advanced. This is how I initialize it. And yeah, I'm pulling out the first thing and adding a float to it. So again, it'd be very easy to ditch that and just return the tensor with one element, and then you could jig that whole thing. Okay, so you don't have general recursion, but JAX does provide you with the kind of primitive structures that you would need to iterate over structures or just iterate in J.
So if that's cont and advanced, then they also supposed to be here.
Yeah. Yes, exactly. They have to be pure functions.
Even with the model.
Right, yeah, so if you go back to the for loop, you see that you weren't doing anything bad inside the for loop. So where was the for loop? There we go. Yeah, so you weren't mutating anything inside the for loop yet. You were working with the I that was provided for you and the accumulator that was provided for you. And you weren't mutating anything. You were simply computing the next values. Yeah, so it's definitely not as flexible as a Python for loop or while loop, but that structure is what allows it to be automatically analyzed, parallelized, put on GPU, auto-diffed, etc. Right, so you're getting a lot for that discipline of using pure functions. Am I lost? Okay, what time is it? 10 o'clock. Yeah, that's fine. So we'll just have a look at this and then we'll break for coffee. Right, so we go to our logistic regression example again, using gradient descent. The file is there, you can just look at it. So you just run it with Python if you've got JAX installed, and it should just run. And so again, you can just look at the code, or you can play with the code, fiddle with it, see if you can break it, improve it, whatever. Let's just have a look at it. So a bunch of imports. Yeah, all the rubbish to read it in and set up your X and Y. But then again, it looks much like, say, the Scala code. We've got a log likelihood function just written using JAX NumPy, which basically looks almost exactly like NumPy, where the MP is replaced with JMP. Okay, so that should look familiar if you've used Python at all. That JIT's okay. But then for the gradient, we don't have to hand code the gradient. We can just say, well, let's have the grad of LL, and it just works. Okay, so that's really nice. And again, we may as well get that just for good measure. And then our one step function takes an initial B and potentially a learning rate, and updates it using the gradient of the log likelihood that we've computed using autodiff. And then the ascend function again, has a sort of similar structure to the Scala and Haskell version. We need some kind of termination criteria. Okay, so we're going to use a while loop for this, right? So we need our termination criteria, which is, you know, have we converged in some sense? And then we've got our one step or step state, where we unpack our state and then advance along. Yeah, so I'm passing, so I guess I should explain that. I'm passing 2 bits of state through so that we can do a convergence check. Yeah. So I'm passing x0 and x1, or current x and previous x, if you like, so that we can do a convergence check, as well as the number of iterations that we've had. And yeah, we advance to get the new state, and then we kind of advance our 2 states along. So we kind of get passed in x1 and x0, and we pass out x2 and x1. Yeah, so we've shifted our states along one, and we're decreasing the number of iterations left by 1. Okay, so we will exit either if we've run out of iterations, or if we converge x to b. Yeah, and then we call our Jack's while loop. And we just make sure we initialize it with 2 very different things, so it doesn't converge instantly. Yeah, then it should be just as before. Yeah, so we're just going to use Jack's while loop to do this iteration for us. Okay, so that's all in Jack's, but then in the end, I'm just using regular Python to bring out what's happening. That's fine. It's all the meat happens in Jack's. Yeah, so I think that's pretty much all there is to say. Yeah. Okay, so I think coffee was supposed to arrive at 10. So I think this is probably a good place to break. So we can come back. I don't know, you can have a play with this, break the coffee, come back 10:40. Does that make sense? Is that all right? Yeah, restart at 10:40, and as usual, I'm happy to take any questions.
We will essentially now. Just a little bit of file. Very you realize that the suites was there. So you have a high confidence. Okay, but you don't have to. So,